Hi, my name is Samantha Guadarrama. I am currently conducting research under Dr. Hosmani, and my research topic is boron biomolecules for medical applications. Boron neutron capture therapy is a promising new and effective form of cancer treatment. It utilizes the boron-10 isotope that undergoes a fission process with the addition of neutron radiation. The boron-10 isotope is preferred over any other boron isotope as it is naturally abundant, meaning it occurs more naturally. And an adequate amount of boron-10 isotope is in the cancer cell is necessary for the effectiveness of the treatment. A carrier molecule is necessary to exploit the abnormal cancer cell physiology to selectively deliver the boron-10 isotopes to the cancer cell, and fluorescence can then be attached to a boronic acid compound, which can be used as a carrier molecule that will allow the product to be seen as it is being distributed throughout the body. The overall goal of our research is to synthesize biocompatible molecules that can be used as carrier molecules throughout boron neutron capture therapy in medical applications. So to begin synthesizing our molecules, we first placed a reaction, a substitution reaction, which was conducted by dissolving 2'7' dichlorofluorocene in dimethylformamide in a round bottom flask. Potassium carbonate was then added as a base to deprotonate the alcohol group, and the deprotonation was necessary to aid in the attachment of the propagyl bromide. The reaction was left to spin for about 3 minutes and then was covered with aluminum foil as the reaction is light sensitive, so we want to ensure that no light gets in. Propagyl bromide was added with a syringe and the reaction was left to spin overnight in 80 degrees Celsius. The next day, a TLC was conducted to ensure that the reaction was ruled complete with hexane and ethyl acetate, and an extraction was then done with deionized water and ethyl acetate, and the organic layer was dried over some sodium sulfate. To further purify our sample, the silica gel column chromatography technique was used with hexane and ethyl acetate, and to ensure that we had obtained our desired product, we further tested with nuclear magnetic resonance. Both cesium carbonate and potassium carbonate were tested to determine which of the two bases would result in a better yield, which happened to be potassium carbonate. Next, the dehydration reaction was done. From the previously synthesized product, we dissolved that in methanol in a round bottom flask. Hydrazine was then added to the reaction as it will open the carbon ring and replace the oxygen with a nitrogen bonded amino group prior to closing the ring again. The reaction was left to spin overnight in 80 degrees Celsius in an oil bath to ensure that the heat was evenly distributed, and the extraction was done the following day in deionized water and ethyl acetate. The organic layer was then dried over sodium sulfate, and the next reaction was then placed. The next reaction was an esterification reaction, which included carboxyl phenyl boronic acid, which was dissolved in dimethylformamide and 4-dimethylaminopyridine. The reaction was left to spin for about 10 minutes, and then 1-ethyl-3,3-dimethylaminopropyl carbodiamide was added while the flask was in dry ice to ensure that the cold temperature was maintained. The reaction was then left to spin for at least 30 minutes, and while it was spinning, the protected 2'7' dichlorofluorocene product was dissolved in dimethylformamide and was then added to the reaction and left to spin overnight in an oil bath once again at 80 degrees Celsius. The following day, TLC was done to ensure the reaction was complete, and the reaction was then extracted with deionized water and ethyl acetate. The organic layer was once again dried with sodium sulfate, and a silica gel column was conducted to further purify the product. Lastly, the final reaction was the cage closing reaction. The 2'7' dichlorofluorocene propagyl bromide was reacted with decaborane and dissolved in anhydrous toluene and acetonitrile. The reaction was left to to spin at 111 degrees Celsius, as that is roughly toluene's boiling point, and we wanted to reach the maximum boiling point. The reaction was then analyzed with TLC to ensure the reaction was complete with pure dichloromethane. The reaction was then extracted, and DI water and ethyl acetate was used, and finally the organic layer was dried once again with the silica gel column, and it was further purified. It was further purified with a silica gel column. As for results, as seen in the graph here, the spectrum showed that we did indeed have 7 peaks, which was the ideal number of peaks that we were going for, a closed carborane 2'7' dichlorofluorocene cage complex. And as for a conclusion, all reactions have been successfully synthesized and have been characterized through proton, carbon, and boron nuclear magnetic resonance. They have also been further analyzed with mass spectrometry. Although we have not finished the project, our future work includes having the carborane cage functionalized with cancer cell receptors such as folic acid, glucose, or cancer recepting sites. And also, too, further biological analysis will have to be conducted on all of the molecules. And yeah, I'm currently working under Alejandra Macias and Sagar Somia as my grad students, and my acknowledgements go out to Dr. Hosmani, Somia, Alejandra, and Thomas.